Right, let's talk about measuring things. For years, coordinate measuring machines, or CMMs, have been the heroes here. Traditionally, they used a touch probe, a sort of highly sensitive mechanical finger. This works splendidly for many things, but sometimes you need a gentler approach. This is where optical probes come into the picture. Imagine trying to measure something incredibly delicate like a tiny electronic component. A touch probe could cause a tiny bit of damage or push the material, giving you a slightly off reading. Optical probes solve this by using light. They measure things without ever making physical contact. This non-contact precision is a game changer in the world of metrology. Now, you might be wondering how these optical probes actually see and measure things. At the heart of most vision probes, you'll find a high-resolution camera. This isn't your average holiday snapper. We're talking about industrial-grade cameras designed for capturing incredibly detailed images. But a camera on its own is just a picture taker. The real intelligence comes from the software that backs it up. This sophisticated software performs complex image processing tasks. It can identify edges with remarkable accuracy, detect changes in surface texture, and pinpoint specific features on the component. To see anything clearly, you need good lighting. Illumination systems are a critical part of any vision probe setup. The high-resolution camera captures a detailed image of the part. The powerful software analyzes that image, extracting precise dimensional information. Right, so we know optical probes use light, but it turns out there isn't just one type of these clever light-based measurers. First up, we have the two-dimensional vision probes. Think of them as a very, very accurate digital camera system mounted on the CMM. They excel at capturing two-dimensional features. Then we have something a bit more three-dimensional in its thinking, laser triangulation sensors. As the name suggests, they use a laser. A laser beam, often a line rather than a single point, is projected onto the surface of the part. A camera, offset at a known angle, looks at where this laser line falls on the object. By using a bit of good old trigonometry, the sensor can calculate the distance to the surface at many points along that laser line, creating a three-dimensional profile. Finally, for the ultimate in surface detail and microtopography, there are white light interferometers. They work by splitting a beam of white light. The shape of these fringes reveals incredibly fine details about the surface texture and height variations. Section 4. The brilliant benefits and the odd little snag. The most obvious and significant advantage of using these optical probes is their non-contact nature. Because optical probes use light, they exert absolutely no physical force on the component. Another major plus point is speed. Optical probes, particularly vision systems and laser scanners, can capture vast amounts of data very quickly. However, it's not all sunshine and perfectly measured roses. Optical probes do have a few limitations. Highly transparent objects like clear glass or some plastics can be tricky because light tends to pass straight through them. Similarly, very shiny mirror-like surfaces can cause problems with reflections. Deep features, narrow slots, or hidden internal geometries can also pose a challenge for optical systems. Touch probes, with their slender styli, can often reach into these nooks and crannies more easily. Sometimes a combination of methods is needed. Section 5. Joining forces, the perfect partnership for a pinpoint precision. Modern coordinate measuring machines are increasingly becoming hybrid systems, capable of using both optical probes and touch probes on the same machine. This hybrid approach is really rather sensible. It allows a manufacturer to harness the strengths of each technology. For instance, you could use a fast optical laser scanner to quickly map the overall shape and form of a large free-form surface. Then for critical small features, deep bores, or areas where the optical sensor might struggle, the CMM can automatically switch to a touch probe to gather that specific data. This flexibility means you can tailor the measurement strategy perfectly to the part in question. Ultimately, the integration of optical probes into CMMs represents a significant enhancement in the field of precision measurement. They haven't entirely replaced touch probes, nor were they ever really meant to. Instead, they've expanded the capabilities of CMMs, allowing them to tackle a wider range of measurement challenges with greater speed and versatility. This perfect partnership between optical and touch probes ensures that manufacturers can achieve pinpoint precision in their measurements. As technology continues to advance, the role of optical probes in modern manufacturing will only grow, offering even greater potential for precision and efficiency. The future of manufacturing is bright, with optical probes leading the way in precision measurement. Let's dive deeper into the applications of optical probes in various industries. Optical probes are widely used in the aerospace industry for inspecting turbine blades and other critical components. In the automotive sector, they ensure the precision of engine parts and body panels. The medical field also benefits from optical probes, particularly in the manufacturing of medical devices and implants. These probes provide the accuracy needed to meet stringent regulatory standards. Additionally, optical probes are used in the electronics industry to inspect circuit boards and semiconductor components. Their non-contact nature makes them ideal for handling delicate and sensitive parts. Overall, the versatility and precision of optical probes make them indispensable in modern manufacturing and quality control processes. Now let's explore the future of optical probes and CMM technology. As technology advances, we can expect even greater integration of artificial intelligence and machine learning in optical probe systems. These advancements will enable more accurate and faster data analysis, leading to improved quality control and manufacturing efficiency. Imagine a world where optical probes can predict potential defects before they even occur, thanks to sophisticated algorithms that learn from every scan. This isn't just a dream, it's the future we're stepping into. Additionally, the development of new materials and manufacturing techniques will drive the need for more sophisticated measurement solutions. Optical probes will continue to evolve, offering higher resolution, better accuracy, and more robust performance in challenging environments. The future of precision measurement is bright, and optical probes will play a crucial role in shaping it. From smarter factories to groundbreaking medical advancements, these tools are paving the way for a more precise and efficient world.